Hi there, my name is Granville Matheson, and I'm going to be producing, I'm going to be presenting Kinfitr. It is for reproducible kinetic modeling of pet data in R, and more recently with BIDS. So getting back to what Graham said earlier, basically, hopefully all all pet imaging tools will be able to just read BIDS data in, and Kinfitr can do this already, but I mean, hopefully this is going to be a reality that in future we can basically select whichever tool we want to use. So firstly, I'll discuss quickly what Kinfitr is. So Kinfitr is an R package for pet kinetic modeling. It contains a bunch of utility functions for doing unit conversions and all the rest. It also contains invasive and reference tissue models, and it allows you to interact with your data using code. There is no graphical user interface, and I will explain why this is in a second. So when I say an R package, I mean that it's written in R and it works within R. R is an open source programming language. It's very popular in data science alongside Python. It was originally written by and for statisticians, but it now has a much wider user base. But as such, it contains a large number of tools for statistical modeling and analysis, for data visualization, as well as for reproducibility. There are 2 papers currently about Kinfitr. Firstly, just introducing the package and talking about some of its functions. And more recently, just accepted the other day in EJNMI Research, is a paper where we compared it to a commercial tool. We used 4 different radioligands, 2 regions per radioligand, and 6 different kinetic models. And we found Pearson's R values of between 0.95 and 1, with a median of 0.99 compared with PMOD. So we believe that it's basically ready to be run in your data. I think I might also mention that the student who did this, Jonathan Cherkassky, he was in fact a medical student with no background in programming and was able to, working part-time, pick it up in a couple of weeks. So the interacting with data using code requirement is not as insurmountable as it might seem. So what Kinfitr does, there are various steps in processing of pet data. So the first step is usually image processing, motion correction, co-registration, ROI delineation, PV correction. Kinfitr does not do any of that. I figure that there are enough different tools that do that we don't need to reinvent the wheel. But that basically produces time activity curves. So Kinfitr works with those. It does do blood processing though. It does do kinetic modeling and all the steps there. And once we've done our kinetic modeling, we have our BP values, our VT values. For all the rest of everything, statistical analysis, tables and figures, well, I've discussed that R is actually designed with all of these things in mind. So we actually do all of this in R, and in fact, even article writing. And I'm going to get back to this and why this plays into things as well. So I talked a lot about reproducibility. It's worth defining exactly what I mean by that. There was a great sketch here, and it's been described as a minimal viable level of a minimal viable standard for computational research, where basically we have the same data and we have the same code, and we should be able to produce the same outcomes. And it sounds really basic and really simplistic, but what it essentially boils down to is that everything can be recorded in code so that the results can be recreated either by me or by independent researchers. So when it comes to independent researchers, it's aimed to increase transparency. So there was a great description. I hope in 20 years, we'll be amazed that scientists once blindly trusted results they couldn't press the run button on. And that's kind of the idea here with reproducibility. But despite all of the upfront work of making sure that everything is instantiated in the code, it also has benefits for me as a researcher and for you. In that this is actually a real email that I received. Sorry, Granville, I discovered an error in the age of patient 16. It should be 49 instead of 55. Do you need to redo the analyses? And the answer was yes, I do need to redo the analyses. But because everything was actually written in code, all I needed to do was change the 49 to a 55, change the 55 to a 49 and press the run button. And all the tables regenerated, all the figures regenerated, and even all the text regenerated that we needed to place in the article. So when it comes to kinetic modeling, we have all sorts of things where we often want to we often want to go back and change things, like change in the T-star time. We want to realize, oh, well, we should have actually fitted VB instead of set it. Or we want to change parameter bounds, figures, tables, article text. You can basically just change all of those things. You can change the data or you can change the code, and you just run everything automatically, and it steps through everything without needing to redo all the steps, as you often need to do in a graphical user interface. Then there's also flexibility during modeling. It allows you to be much more flexible. It also allows error detection to be much more simple, and for correction to be much more straightforward. There have been, I mean, if an error occurred in an old Excel table where someone sorted the wrong column at some point in the past, that information is gone and you don't know when it took place, and you have to sift through old files. When it comes to doing it in code, and it's almost never that we found a perfect document when we've been going through everything, like, oh, wait, here, there's a little mistake here. So it allows you to very easily detect your errors. Lastly, it allows for transparency of all steps taken with full documentation as a byproduct. So without needing to concentrate on actually being transparent, it is, and it documents everything, which is now a thing that we've been focusing on recently, with needing to actually document our research steps. So that is where BIDS comes into the picture. So BIDS, by providing a completely standardized way of structuring data, it allows for automatic and uniform data ingestion from the raw data, which actually makes it much more easy to do processing of our data. So I'm going to go through a little demo in a second, but just before I do, you can get Kinfitr from my GitHub, which is, you can basically follow the link at the top, and there are instructions there for how to download it, how to use it, how to do, how to load the data, how to do whatever. There's also all the other links that we need. There is also a Docker image, so that means it can be downloaded and run within a virtual environment without any installation. So I know that there are people in Gothenburg actually running it on their server without needing to install anything. There are also some vignettes to see its usage. So it basically steps through a typical analysis where you run over subjects and over different regions and how to do everything, as well as a binder sandbox, which allows you to basically play with the analysis, with the data in your browser without needing to download or install anything. So it allows you to just get a feel for it before you want to actually download anything. So now I'll move on to our demo. Let's just hope that the demo gods are with us. Let me see. Here we go. So here is, so with the pig data that we've seen a number of times today, this is a little analysis that I prepared that goes through that. So basically, this is the code that I've written. We just load some libraries, we parse the data, and we do all the things. I'll compile everything in a second. I just wanted to show something before I do. So we put together a table as well as some text at the bottom. So the model with the highest VT value was, and then we programmatically define this in the text with a value of, and we programmatically define that in the text. So basically we can arrange it. So now I'll compile it. And while it compiles, I'll talk a little bit more. So basically this allows us to write key passages of the article, or even to write the whole article itself, where every value in the article is basically defined programmatically that we need to. So when we get comments from reviewers, we simply change the things that need to be changed, and we could recompile everything, and all the figures are there, all the tables are there, and everything is there exactly as we wish. So now we've run all the code afresh. We have now loaded some libraries. We set the study path, so I've put this in the same BIDS directory. As like following on from Graham's comments, what is like in terms of motivation for adopting BIDS, this will hopefully be a reality in just about every pet imaging tool in the future. At the moment, it certainly is a reality of mine, and I will be releasing this version in the coming week, which basically conforms to the newest version of the PET standard. So we just BIDS, parse study, study path, and everything is in. So now we add the tags to our data. So these are actually created with an external tool. So presumably you can run like a BIDS, some kind of BIDS image processing tool, such as Appian, which can even run as a BIDS app to define your tags. We then add these tags to our data, and we have our data that looks like this. So in this data set, we only have one image, but we could have as many as we like, and we can actually iterate through all of them. We have session, subject, task, acquisition, file data, pet info, blood data, and tag times. If we want to start looking at our blood data, we just load it up and plot it. So because everything was stored in a completely uniform fashion, we've already been able to process it and interpolate everything. So here we have the blood plasma ratio, which is a very straight line. We have the parent fraction, which could do with a little bit of smoothing. So let's fit some models to it. We have a parent fraction, we pull out the raw data, we fit an exponential curve to it, and we add it back. We pull out a blood to plasma ratio, we fit a linear model. So this is actually not part of Kinfitr, this is just within R as a bonus, because R is good at statistical modeling. And we add it back into the blood data object, and we have our beautiful blood data curve. So we have a straight line through the blood plasma ratio, we have our smooth line through the parent fraction, and we have our resulting arterial input function after all of these, after basically being multiplied through everything else. So we can then, just to show, I'll show fitting a few models. We create an interpolated blood data object, we create some weights, we fit the delay using the first 5 minutes, we pull out the delay value that we fit, and then we fit a two tissue compartment model, a Logan, and an MA1. I've not shown their T-star finder tools, so you can actually graphically decide what the best T-star value should be, and I've decided on 15, 13 frames. And then we plot our images, there are plot tools, and we just see one tissue compartment model is clearly underfitting, 2 TCM is doing okay, Logan is doing fine, and MA1 is doing fine. Then I showed you at the end, the output. We maybe want to create our table for our paper. Of course, we wouldn't want to produce a table like this, but this works. So we have model, we have our VT value, and we have our percentage standard error, and then our programmatic text. The model with the highest VT value was MA1 with a value of 10.04. So in this way, we can basically run our analyses, we document everything as we go, we can share these documents and this code, and if we share alongside the data, then everyone else can do this as well. And by having the data in the BIDS structure, we're able to automatically parse the data and run everything accordingly.